This video shows you some tools for assessing the normality of a distribution. So what is normal? The normal distributions provide pretty good models for distributions of real data, either biological data or, for example, manufacturing data. When you have a 9-ounce bag of potato chips, it won't always exactly weigh 9 ounces, but the distribution of those weights will be normal, centered around 9 ounces. So some common examples of non-normal distributions include things like economic variables, income, or sometimes lifespan variables like how long a refrigerator is expected to last, typically non-normal. So why is it so important to have these distinctions? In the latter part of this course, we'll use various statistical inference procedures to try and answer questions, and these tests involve sampling people or objects and recording data to gain insights into the population from which they come. Many of these procedures are based on the assumption that the host population is approximately normally distributed. And that's why we need methods for assessing normality. We want to check to see whether using those tools, those statistical procedures, we want to see whether it's appropriate to use those for certain situations. So the first method of assessing normality is just to eyeball the distribution. You could look at a histogram or a stem and leaf plot and check to see if it has that hallmark bell-shaped curve, symmetric about the mean. One way you can improve this method is to mark off the points x bar, remember that's the mean plus or minus 1 standard deviation, plus or minus 2 standard deviations, and then compare the count of observations within each of those intervals to the 68, 95, 99.7 rule. I can walk you through an example of that. Here we had vocabulary scores. Clearly they're symmetrical, they follow that bell-shaped curve, so it would be reasonable to expect that they're normally distributed. And then if we were to look at the individual scores, the mean of all of those 947s was 6.85 with a standard deviation of about 1.6. And so if you mark off on a number line and then count the number of observations, we should have about 68% of scores between one standard deviation below and one standard deviation above the mean. And we would continue that for the 95th percentiles and 99.7s. Here's another example. This is sample problem 2.5 in your textbook. Here we have something where it's not exactly clear that the histogram shows us a normal distribution. Because there are so few data points, we need another method for assessing normality. And so the second method is called a normal probability plot, or NPP. The basic idea is to arrange all of the data points from smallest to largest, and then record each data point's percentile. Remember, percentiles are the percent of scores at or below a certain given point. Then you are to find the z-scores that correspond with those percentiles, and then plot each data point against its corresponding z-score. Now this seems kind of technical, seems kind of sophisticated, and some technology uses even more sophisticated versions of this same idea. The suggestion is let a calculator or computer create the normal probability plot for you. What's really important is how to interpret these normal probability plots. So if the points on a normal probability plot lie close to a straight line, then that plot indicates that the data are normal, or at least approximately normal. Any systematic deviations from that straight line indicate non-normal distributions. Outliers will appear as points that are far away from the overall pattern. Let's walk through a couple of examples of normal probability plots. Here we have a distribution that is relatively normal. You'll see there's sort of a stepping stone pattern for some of the points in the middle. We call that granularity, and that's only because we have a couple of repeated observations. It's really no big deal. It's not a large deviation from normality. Here we have another normal probability plot that clearly indicates non-normal data. In fact, these data are right skewed. When the largest observations fall above a line drawn through the main body of the points, that indicates right skew. Alternatively, left skew is evident when the smallest observations fall below a line drawn through the main body of points. Here's another example of a pretty normal looking distribution. Again, there's a little bit of wiggle, but that shouldn't cause you to overreact. When examining a normal probability plot, you're looking for shapes that show clear departures from normality. Any time that most of the points seem to follow a line, then we're pretty good to say that that's a normal distribution. And here we have an example of an extreme outlier. Most of the data follow a normal distribution, but there's one extreme outlier there. In the next series of videos, you'll be shown how to create a normal probability plot using your calculator.